Alright, so here we have 8.3 Laws of Logarithms. In this section I'm going to do a very quick video here. This is not going to be a full-length lecture, it's going to be a real quick video, so we're going to go through this real quick. Now, my question is in my class here is, how are the following logs related? I threw up this on the screen: log of 16 base 2, log of 32 base 2, log of 8 base 2, log of 2 base 2, and log of 4 base 2. And what I did was I also gave them the values of these logs. You shouldn't need a calculator for this, because you should know that this log of 16 base 2 means 2 to the power of something is 16, and that something is 4, so that's the value of this logarithm. Now, they noticed that there were some similarities here. There were some connections between these numbers. And 4 minus 1 is 3. So if we look at this 4 right here, and this 1 right here, and this 3 right here, if we write those numbers as their logarithms, we see something interesting. We see that this logarithm is of 16, this one is of 2, and the answer is of 8. Little connection there. This one over here, if we take the logarithms of these numbers above, we get log of 32 minus log of 4 equals log of 8. 32, 4, 8. How are they related? We noticed that these numbers themselves are when they're divided, they give the number that's in the resulting log. Consequently, we also found out that when we add the numbers and we replace the logs for those numbers, we see 8 and 2 equals 16. 8 and 4 equals 32, which gives rise to the product and the quotient laws of logarithms. So I'm just going to show that in the screen here now. So any number that can be written as a factor of 2 or more factors can also be written as the sum of their individual logarithms. That's basically what this says. So if we have log of, let's say we have log of 100, this can be written as log of some factor of 100 plus the log of the other factor of 100. So that's 50 and 2, or that's 10 and 10, right? 25 and 4. All of that, that all makes that all adds up. So you can check that out, and of course here's the quotient rule, similar. Now m, n, and the base c all must need to be positive, which we'll explain in a future lesson. The third law that we're going to talk about in this brief video is the power law of logarithms you see down here. Now before I give it to you, I want to show you, well, I guess no, that's part of the other example. Okay, so here's where I kind of develop this now. So with the power law, here I've given you two logs that are equal to each other. I've just written 64 a little different way here. I've written it as 8 squared. Okay. Now I asked my students, I said, can you come up with some kind of rule, the power rule, or the power law? You guys come up with the power law given that these two are equal. So what can we do with this exponent that also works for this one? And this is what they came up with. They tried, some of them tried, log of 64 equals the log of 8 here, and then they squared that. Well, does that make sense? This is 6 over here. This is 3. So does 6 equal 3 squared? The answer was no. So that was a bust. But they did notice that if this 2 was instead of being a square, if this was 2 times, then it totally works out. You see, this is the log of 64 base 2 is 6. And if we did 2 times this log, which is 3, then that would be equal. So they tried it over here. The log of 27 base 3 is 3, because 3 cubed is 27. And they brought that 3 down here, evaluated this part of the log, and that's 1. And guess what? That works out too. So that brings us to the power law of logarithms, which I will show you in a second. So here are the product, quotient, and power rules here now. So if you can see that right here, this p, that's the exponent on the power, it can be written as a coefficient, really, in front, or as a factor here. So this p can be brought out of the exponent position. This is that is the big reason why logarithms are so useful, is because this value, whether it's a monomial or an expression, can be brought down to the front, and it can be a regular old algebraic multiplicator of this. That's huge. And that leads us to what we're going to be studying really more in depth in the next section, that these logarithms can be applied. So if I want to solve this exponential equation, I can apply the logarithm to both sides whoops. And then because of this rule, that x can now be brought down in front, and this becomes x times log of 8. I divide by log of 8, and then I get x equals this value right here. See how easy that is? You can't make these the same base, so why even try that, right? Now we have logs, and these properties are going to help us solve that. Okay. One of the things that we also did is use these laws now to write an expression of logarithms as a single logarithm. Notice what I did here in this example A. This 2, I used the power rule to bring it down, which made 2 log x base 7. This is already 1 log x base 7. And this over here, if you view this as a multiplicator here, that's minus 5 over 2 log x base 7. And because all of these are really the exact same log, they're just different numbers of them, we don't have to reach too far into our tool belt here to just add up these coefficients. And you get 2 plus 1 minus 2.5 is 1/2 log x. That's the easy way. If you didn't see that, then what you could do is use the other laws of logarithms, and you could say, well, I have all the same base, okay, 7 all the way around. I have x squared plus x, and then I have minus x to the 5 over 2. And so this represents a multiplication and then a division. So we can write it like this, a single logarithm like this. When we simplify that, 3 minus 2.5 is x to the 1/2. Of course, this 1/2 now can be written as a coefficient. Boom, get the same answer. And for those of you that have the textbook, Pre-Calculus 12 by McGraw-Hill Ryerson, there's an assignment that you can do. So that's your quick lesson on 8.3.